This video is on the hypothesis test of a correlation coefficient. The correlation coefficient can go between -1 and +1. -1 is a perfect negative correlation, which is when you end up with a scatter plot like this, where they all follow a straight line. A perfect positive is when the dots perfectly follow this rising line. And then 0 is just no correlation, which is when you have just a blob. The dots don't rise or fall from left to right. When we make our scatter plot, we're making it with our sample. We're making it with our recruited participants. But we want to know, what would the scatter plot look like if we actually collected data from all members of the population? And we actually don't know what it would look like because we haven't been able to collect that data. But we can still use our sample to hopefully make a decision about what we think it would look like. We have a null hypothesis that there's no correlation in the population, meaning the null hypothesis says that the population scatter plot would look like this. It would just be no correlation at all, which would mean that there's zero correlation in the population. The alternative hypothesis is everything except for that possibility. The alternative says that if we made the population scatter plot, we would see at least some correlation in the scatter plot, meaning the population correlation wouldn't be zero. When we calculate the correlation coefficient of our sample, and we calculate its value, the sample correlation coefficient is likely to be somewhere near to the population correlation coefficient. Just like how the mean of a sample is likely to be close to the mean of the population. But once again, that's assuming that the sample is random. If you randomly select a sample, then the sample correlation coefficient is more likely to be close to the population coefficient, and it's less likely to be further from the population coefficient. So let's imagine that this red X is the population correlation coefficient, which is unknown. The correlation coefficient that we get from our sample is likely to fall within a certain range of the population correlation coefficient, meaning the sample coefficient is unlikely to be too far below the population coefficient down here. It's unlikely to be too far above the population coefficient up here. It's likely to be somewhere within a certain range. If the null hypothesis is true, and the population has no correlation in it, meaning the population correlation coefficient is 0, the sample coefficient is likely to be somewhere near 0. The expected range is around 0. So if the null hypothesis is true, you're likely to get a fairly weak correlation coefficient in your sample, somewhere near 0. What if the red X, meaning the population correlation coefficient, is not at 0? What if it's down here at -0.4? Well, now the null hypothesis isn't true anymore because the population correlation is not at 0. If this red X, which is the population correlation coefficient, is anywhere but 0, then the alternative is true. In this situation, there's a negative correlation in the population because the population correlation is at -0.4. When this is the case, the sample correlation is likely to be somewhere near that number down here. Which means that the sample correlation coefficient is not as likely to be around 0 anymore, because the population correlation coefficient is actually in the negative area. So when the population correlation is down in the negative area, you're more likely to get a sample correlation further down into the negative area down here. If the null hypothesis is wrong and the population correlation is somewhere up here in the positive area, you're likely to get a sample somewhere in the positive area up here around the actual population correlation. Which is in the positive area. So the main point is, if the null hypothesis is true, and the population correlation coefficient, the red X, is actually at 0, the sample correlation is likely to be somewhere near 0. Which is why, if you get a correlation in your sample that's close to 0, meaning somewhere down here, and it's very weak, you can't reject the null hypothesis. You're pretty much stuck with the null hypothesis that the population correlation is 0, because these outcomes in here are expected to happen in that situation. These types of correlations down here are expected to happen if the population is at 0, so they don't allow you to reject that possibility. But if you get an outcome, a sample correlation that's further to the negative end out here, it's no longer in the range that would be expected in the null hypothesis situation. If the population correlation was at 0, a sample correlation this far to the negative end would not be expected, because it's too far from 0. Which is why if you get an outcome this far below 0, you're allowed to reject this possibility, the null hypothesis, and say that there appears to be a negative correlation in the population. If you get a sample correlation that's far enough toward the positive end up here, you know that it's outside of the range that would be expected if the null hypothesis was true, which means that you conclude that there is a positive correlation in the population. So how do you know if your sample correlation is far enough from 0 to no longer be in the expected range of the null hypothesis? Well, if it reaches the positive critical value, which is a cutoff somewhere on this end of the number line, that means that your sample correlation is so far above 0 that it would not be likely in the null hypothesis situation. You reject the null hypothesis of no correlation and say that there's a positive correlation in the population. If your sample correlation is far enough below 0 to reach the negative critical value, your outcome is unlikely in the null situation, which means the null is rejected, and you say that there is a negative correlation in the population.